Hi everyone, my name is Sebastian Olsson. I'm going to talk about protecting your app data from attackers, whatever that means. I develop and audit code mostly, source code of different types, mostly Java nowadays, but also some C++ and other stuff. Today we're going to talk about where data lives in different types of applications and how to protect it from, for example, being read by someone who shouldn't, or being modified, or being trusted when it shouldn't be. It's going to be more focused on general tips and classes of protections. So not code examples for specific languages, more of ideas to help you identify problems in your environments when you're developing. So I'm going to set the scene just to illustrate my view of the world. So the classical view that people have often is that you have a client of some sort, and then you have a server, and the client calls the server, and the server stores something in a database, some user information or something. Or if you're more like modern, I don't know if HTML5 is cool anymore. It's been around for years now, I suppose. Whatever the cool kids are doing right now. They might have some data in the client as well, some cookies or some local storage or file system or what have you, or an application. In reality, it might be something that's more similar to this, in the sense that you might have a client, desktop client as well. You might have multiple servers. The servers might be calling each other, and they might be exposed to the internet as well. You might have interfaces that you don't think about, such as backup between the desktop client and the mobile client. That will become an interface as well, where you can post data to the other node by backing it up via some interface. So in this case, we could view it as nodes of some sort. Nodes that store data and communicate with the world, and that would apply to everything pretty much to make it simpler or harder. So in this case, mobile apps, web browsers, embedded systems, what have you. So it's typically an application of some sort that has a lot of logic that you write. You have some storage where you store stuff, and then you communicate with the other nodes in this scary black cloud over there. So in this, just to complicate stuff, I'm going to use other terms. I'm going to call it data at rest, and I'm going to call it business interfaces and data in transit. Still other nodes, though, in the spot over there. And we will have probably a bunch of attack vectors on each of these, like vulnerabilities in the storage unit, or middleware vulnerabilities, someone tampering with our data, injecting something in our build process to destroy our application, or something like that. So we're going to talk about the different classes of protection for these problems, starting with data at rest in this case. So let's look at data at rest. Let's talk about sandboxing. It's a concept that's used a lot, for example, for mobile applications, but and for example, a Java application running in a browser, which people hopefully aren't doing anymore. But in this case, I want to say like sandboxing might be some sort of software boundary that you think might apply, but doesn't necessarily. So that could be virtualization, Android separation between Android or iPhone apps. Definitely containerization, such as Docker and Core OS, application servers of some sort. Cookie storage could be seen as a sandbox. You expect your cookies to only be read and modified by your site, but perhaps someone could modify the cookie. Definitely the user, but perhaps some other site as well. Or the local storage of your HTML or JavaScript-based application. So a common problem would, of course, be not validating stored data. That's the obvious thing that people don't do. They think that just because something is on your file system or is in your sandbox, it's something that we can just feed into the most sensitive part of the system. But that's not really true. We need to be able to validate even stored data of sorts. We could have a lot of problems. Of course, if we trust incorrect data, that could blow up in all sorts of ways. We could have the classical stored cross-site scripting example that Andreas touched on, where you store data in one context and read it in another. And if you don't have your XSS protection in the part where you read it, you might get a XSS problem there, or some sort of second-level SQL injection or something like that. You might, of course, have compatibility problems. That's not necessarily a security problem. It could be just a bug in your application, because you want to find out the incompatibilities as early as possible, like Andreas also talked about, finding the bugs at an early stage. And the data could definitely change between validation and usage. Typically for a file system, if you read something to validate it, say it's okay, and then read it again to use it, the data might have changed in between. That's a common problem for example, different sorts of signature validations on file systems, where systems validate the signature on the file, malware or something switches out the file in between the validation and the actual usage, and the system thinks that the file that's running is actually validated when it isn't. So, of course, you need input validation of some sort, and you need to validate data rigorously. And if it's very sensitive, you might also want to add some sort of data authentication, a signature on the data. I don't think that's normally the case. Very few use cases where actually signing your own application data is something that you need to do, but it's a possibility at least. But the lowest level you need is to have validation of the actual data that you're going to use. Such as in the file system case, we would want to have some sort of actual immutable data that we read up and validated before using it. Another common problem would be relying solely on the isolation of the of the sandbox storage. Perhaps it is publicly available when you think it isn't. A similar problem would be using some sort of global file system, which is a common problem. In, for example, Android, people like to store stuff at an SD card that's world readable and world writable. So if you install some other application, they can modify your application data that you happily then read into your application, and, well, bad things could happen. In this case, the problems would be all of the previous problems, but also your credentials and secrets could be extracted, perhaps. And that might be a problem. And it also might be possible to modify your data to get access to interfaces or get access to stuff that you shouldn't be able to. So you need probably the same protections as the previous slide, that is validation and perhaps authentication. Definitely you should look into, of course, the read-write rights, which is a hard thing to say for me. You shouldn't store sensitive data in a world-readable area. And that might be obvious, and it's kind of weird because a lot of these things feel very obvious, and yet they pop up all the time in pretty much every application. If you're storing passwords of some sort, you should, of course, store them in a securely hashed format. But of course, everyone does that, right? Well, a lot of people don't, but it's very important. If you only need to verify a password, of course, you don't need to store the password, and that goes for other secrets as well. You could, of course, encrypt the data if you want to. There are fewer use cases for that, at least in the application layer. If it's possible, you should always opt to get the highest encryption of the platform you're using. But sometimes you might want to do your own encryption and authentication, but that's for fewer use cases, I would say. And if you're on a mobile platform, of course, you should leverage the platform to set as strict permissions as possible. for example, iOS keychain this device only, and making sure, for example, on Android that things aren't exported that shouldn't be. Because that goes into another common problem in these situations, which is some sort of capability leak, where one app could call the other application and we use that application's privileges to read or modify, for example, storage or interfaces. Could be called some sort of confused deputy situation where the storage permissions are limited to app 1, but by leveraging app 1, app 2 gets the same permissions. So in this situation, we're impersonating another app by using an interface, and that's very common because people tend to add some sort of private interface or implicit interface to their application that's supposed to be only used from the application, but could be called from another application. If we're in the mobile world, it might be, for example, on Android, content providers. If you have a content provider in Android, it could be readable from, perhaps from other applications, and they can read and modify your data without you knowing. Often you can pretty much get a view of the application's file system, so to speak. So, of course, you need to make sure that those interfaces are not available to the outside. And if they are available to the outside, they have to have authentication and, of course, then authorization. There shouldn't be interfaces that could be called from some weird application where you don't know who's calling and if they're allowed to. And another problem in this vein would be the actual backup functionality that people tend to not think about on. And this could be a mobile system or a server system or what have you. So when you back up sensitive data, that data will be added to the backup, which of course could be a problem. Because perhaps you weren't really ready for that, because if we back up the application, it might be possible to retrieve that backup from some sort of other location and thus get the sensitive data. Also, the data might be modified externally. In the desktop case, for example, I have a mobile application and a desktop application. I get the backup of the data to the desktop application where I can more freely modify the data. And then when it's loaded back to the mobile application, it can wreak havoc. So if you don't need backup, you perhaps could just remove it. And of course, if you're really paranoid, you could also protect things in memory. I think that's very rarely needed. I don't think that's a big use case at all, because it's extremely hard to do. If you have sensitive data, you could theoretically write garbage into memory, but it's very hard to do in a systems language. It might just be optimized away or removed, and it's even harder to do in a managed language, such as Java. The same goes for encrypting things in memory. So that could be, it's very hard to do, and it's probably not a good bang for buck, so to speak. And sometimes people try to avoid, for example, string interning in string pools, also such as in Java, which is the reason for a lot of interfaces taking characters arrays instead of strings, because strings could be pooled in a global pool. But I mean, that's not probably going to be the biggest problem your application has. So if someone talks about memory protection, that's fine if you had all the other protections in place, but I don't think it's normally useful. So when we set all the very strict settings for our data at rest, we want to look at the business interfaces and the actual logic. And then we got to think about, do we trust everything that we get in an interface? Probably not, because we probably don't trust everything that people tell us. So we need to think about how to protect our interfaces. To be able to do that, we need to have some sort of authentication that is answering the question, who are you? And when we actually know who you are, that's the first point where we can actually do an authorization, that is to check if you're actually allowed to make the call. Because if you don't know who's calling, you can't really decide if they're allowed to make the call. And of course, we need to set this in the and we need to validate our interface against the domain rules that we have. That is, we need to look at what's acceptable input for us. Is it possible to, for example, then transfer minus 1,000 euros, or is that invalid in our domain? And we need to really, really strictly limit the interfaces that are globally faced, well, or exported in any way. That's probably the simplest way to protect these interfaces, because a fancy REST mapper can really bite, and it bites hard. If we look at a typical interface that's dynamically generated via some really quick, agile, fantastic framework, I get to see my user info, and I'm user 123456. So obviously the URL is /userinfo 123456. And can someone see something weird about this? Yeah, of course, there's HTTP. That is true. That is that's interesting. Yeah, that's not actually the problem in this case. That's one of the problems. Yeah, sure. I got to change that. Thank you. Something else? The username. Yeah, perhaps. What's happening here? Why is this a parameter? Why is this a part of the URL? And what would happen if I would enter 123454, for example, or 123458? Hopefully, there will be an authorization check that checks that I'm user 123456. I can't do this call for 123454. But more commonly, because this exists in pretty much any application that is pen tested, you just get the user info for user 123454, which is bad. And of course, you will get solutions, and a lot of people would suggest that, oh, you use a UID, don't use the auto-incremented database index. But that's not a solution to the problem, because that's not the point of a UID. A UID is not a security solution in this case, because URLs aren't meant to be secret. A UID will make it harder to guess. I mean, if I were to just brute force this, it would be like, yeah, finding two equal snowflakes or something. But I probably don't have to brute force it, because I can probably find this UID somewhere else in the interface, or in the in another return value of another object. If we have a forum someplace, I can see that someone has posted something, and then I can find their UID, and then I can look at their user info. So it doesn't solve the problem. I need to somehow remove this parameter. For example, in this case, user info current or user info would give me my user info, where the authentication comes from the session, and the authorization, of course, must take place, because perhaps I'm not the user that's allowed to view his user info. But at least there's no reason why I should be able to actually have this parameter to modify, because all the combinations of parameters and the context need to be validated in some way. And that's really annoying, because that's quite a few degrees of freedom. And you have to do this validation against your business rules. Is this combination valid for our business? It's horrible. So the simplest solution is to have fewer parameters and fewer functions, which might be hard to tell the product owner. I have unsuccessfully tried to implement a strategy where if you add a function, you need to remove another function. It hasn't really worked so far, but I mean, that could be a good concept of some sort. But seriously, parts of this is not about someone asking for a function, because the product owner didn't ask, I want a function where I can list, where users can list any user's user info. They want a function where they can list their user info. So in that case, it's you as a developer who chose to add this interface, because it was simple. You could use the same interface for your unit tests or something, but you really need to think about externally facing interfaces in a different way than internal interfaces. So in this case, of course, the parameters shouldn't exist. So just sit down and meditate for a while on each interface and try to figure out, do I really need these parameters? Because you could probably scale back a few and reduce complexity and also remove a few security problems. And one thing I think that people don't really think about is return values, especially when it comes to REST mappers. Because every return value of some sort is an information leakage. Because it would make it easier for me to do this direct object reference attack that I did earlier in PowerPoint format. If I could find out what the other user's IDs or UIDs are. And it's very common that you use a REST mapper, take your domain object, and then just serialize it to JSON or something. And then you use it in some sort of AJAX call, and you just filter out what you want. But if you listen or actually read the calls that are being made, you get this huge document tree with, just every object that's linked by this object. And it's an extreme information leakage. Sometimes it's keys, it's anything. And it's impossible to keep this secure if you're serializing your domain objects. Because each time you modify the domain object, you're actually modifying the output of the JSON data in this case. And it's not certain that anyone modifying that data realizes that they also are sending it to a client. So it's fine to use a JSON mapper, for example, and to serialize objects. But if you do so, you need to have a separate tree of objects that you're serializing where you specify which objects you're actually using. You can't take the domain objects and just serialize them. It has to be a manual process of selecting the data that you want to send out to the world. So I keep getting back to this business rules thing, but you really need to validate according to the business rules. And you always have to perform an authorization check, obviously. So the simplest thing is really ask yourself, why does this parameter or this return value exist? And if there isn't a good reason, then it shouldn't exist. And of course, you need to look into your middleware libraries, because often middleware is the first line of defense when it comes to interfaces, because they're often parsed, or you have some sort of SOAP library, or you have an XML parser. That's not too uncommon that they're vulnerable to, for example, external entity parsing, where I can just read out any file on your file system by specifying an external entity and an XML document. So don't add third-party parsers unless you need them. And you really need to trust them if you're going to feed unvalidated data into them. Moving on to the actual unvalidated data that I'm going to get into my business interface. So the most common mistake people do with TLS or HTTPS is not using TLS or HTTPS. There's really no reason not to for pretty much any interface. I don't know of any, at least, because there are use cases for it. Even if it's a public or non-secret interface, you still want to make sure you're reading data from the correct node. So that's a big problem. So the first step people often do is, we don't want to have the extreme load of using TLS on the full site. So we'll just have this super secure logged in zone where people can be logged in and feel secure and cozy. So you just have to go to the front page and click log on. Well, that doesn't work at all, because in that case, someone could just strip out the HTTPS on the link to the logged in zone. And even if it's only served by HTTPS, you'd only be having encrypted and authenticated communication with the attacker. But I mean, the traffic to the attacker would be really secure. So that's something to be cozy about, at least. So if you want to use TLS, you need to use it exclusively. Same goes for the fallback situation, where you offer both HTTP and HTTPS. And a lot of people don't realize that they have, even if they think they only have HTTPS, they often have port 80 with over HTTP enabled as well. And if you're offering the fallback, it's even easier to block out the traffic over HTTP and falling back to using HTTPS. Sorry, block out HTTPS and fall back to using HTTP. So, example protections in transit would be, of course, TLS. You could have some sort of custom end-to-end encryption. You probably shouldn't. Well, you could, but then you should have it as an addition. You could, of course, have physical separation. You can have your own separate network or air-gapped network. I think most people want to be on the internet these days, so that's probably not a solution. But the protections are pretty similar to those for data at rest. So if we're looking at TLS or SSL, well, it's called TLS nowadays. It's been quite a while. Offers, of course, a lot of different parts. People generally only think about the confidentiality, which is the encryption, and that's fine. Not fine to only think about that, but I mean, encryption is nice. It's awesome. But the thing is, encryption isn't worth very much without authenticity and integrity, because I need to know that I'm talking to the right person, and I need to know that no one has modified the traffic. I don't only need to know that it's encrypted, because I could be talking to an attacker instead. So I need to verify that. In a typical TLS case, the client would start the transit by calling the server, and the server will respond with an X509 certificate, for example, containing the domain name, so the client can validate that it's correct domain, and then they can continue the handshake and establish a channel. So this certificate is, of course, validated against a list of trusted certificate authorities. And if there were to be a man in the middle that would send some other certificate, or would send the correct certificate but wouldn't sign the response correctly, the connection wouldn't be established, of course, because the server certificate contains the public key and the host name, and only the server has the corresponding private key. So the SSL connection would fail in this case, unless you remove authenticity from TLS. Because there could be some problems with TLS, of course. A lot of people complain about that it's very complex. It has legacy support, a lot of support for all sorts of weird stuff. It's built more for browsers than for applications. I think a huge problem could be that a lot of users could and can and do actively choose to bypass certificate validation. That is server authentication. It's a problem that a lot of frameworks actually allow you to do that. Weak cipher suites and SSL version can, of course, degrade security. These days, hopefully, you could stick to TLS 1.1 and 1.2 at least, and a limited set of cipher suites. You could, of course, try to scan your sites with all different sorts of scanning sites that are, well, varying degree of good, I suppose. But I mean, you could at least get a view of which ciphers you're using, because often I think people don't even know what's enabled. Client authentication is nice, but it's not nice because it's very hard to implement. So most often you will fall back to authenticating the server well, with the handshake of TLS, and then you have to actually authenticate the client via username and password in the application layer. So in that case, you need the confidentiality, because otherwise the password would leak. If you had client authentication in the handshake, you could, in some sense, implement a secure protocol that doesn't have confidentiality if you don't send anything that's secret on your channel, which is unlikely. And of course, there has been a few platform vulnerabilities like go to fail and heartbleed. Those are not problems with TLS. Those are implementation problems. You could argue that, for example, with heartbleed, it was an unnecessary feature added to TLS that, when implemented, led to a problem. But it's not a problem with TLS in itself. So a lot of people get, of course, no one would do this, but yet they do all the time, especially on Android and iOS, is they get a certificate validation problem, and then they go to Stack Overflow, input the exception, and they find this fantastic solution. It has 300 upvotes, a green bar, and everyone says, "Thank you very much, you saved my day." But it's it's not a good idea. So don't try this at home, of course. You could try it at home, but never try it at work. Because you can't remove certificate validation. There's no valid case for removing certificate validation. There really isn't. You could limit what you trust, of course. You could pin certificates, and you can really try to nail it down. But there's really no use case, I think, where removing certificate validation is valid. There are people who think that, but I strongly disagree. So if you're going to implement your own, for example, in this case, trust manager, you should really see that you know what you're doing and make sure that multiple sources agree on it. Because otherwise, you've just wasted a lot of time implementing TLS because you haven't implemented TLS. So you could do something more fun, like sit in the sun or something. And just like I said, only confidentiality isn't enough. So what can you do? Well, I think it's pretty simple. You can use TLS. It's what we've got, and it's worked out fairly good so far. You could try to prevent your weak versions. There should be no SSL version at all, and hopefully, if you're really lucky, you could stick to TLS 1.2, but you probably can't. But I mean, at least newer TLS versions, and try to limit, for example, we're not supposed to allow RC4 these days, are we? So try to limit the ciphers that you allow, and at least get a picture. At least you should know which ciphers you allow, because a lot of people probably don't. They use some sort of standard or something coming with the platform, and it's very easy to just scan your site with even OpenSSL command line tool to find out what you're actually supporting. Certificate validation is really integral to TLS, so you should never bypass it. But you could possibly limit it if you know what you're doing. So you could set a more narrow cert pinning, of course. That's fine. I think it should be simpler to do in most platforms than it is. So it could be quite tricky. And try to stay informed on platform vulnerabilities. Of course, keep up to date. One thing is, for example, Java has had, in pretty much every critical patch update that Oracle has had for the last few years, there have been more or less serious fixes in the TLS implementations. And the last critical patch update for Java 7, and that is free, just came a month ago, I would say. And there are no more critical patch updates for Java 7 unless you're willing to pay. So in that case, you need to move to Java 8 or at least get a license for updates, because there will be more patches, for example, of in the Java TLS implementation. And if you're using HTTP, of course, you can use the measures available, like strict transport security, which is where you, via header, specify that the next time you visit a site, it should only be over TLS or HTTPS. That's nice. Of course, it has an obvious bootstrapping problem with the fact that the first time you visit the site, it could be over something that's not TLS. But the next time, you don't have to write HTTPS in front of the address. You will still get it if your browser supports it. And there's HTTP public key pinning, where you, via header from the server, specify a list of public keys that this server is allowed to sign messages with. So you can have, for example, 4 public keys, where, for example, the first one is the actual certificate that you're using right now. And the idea is that if you need to revoke your certificate, you can have a stored public key or a couple of stored public key in a safe somewhere, and then you can just issue a new certificate for that other public key, because otherwise you would end up with a situation where you don't have a valid private key yet. for your certificate, and no one can access your site because they've pinned your site to certificates that you don't have valid keys for. So you should have a couple of keys in that case. So TLS is your best bet probably, but it doesn't protect your business logic. That's kind of common that people think that they can protect their interface or their secret implementation by using TLS and certificate pinning. You're only making it, creating a minor inconvenience for someone who wants to read the traffic. It's fine to do, but you can't rely on it because those interfaces will be read because traffic can be extracted. Cert pinning is most often quite simple to remove. So you shouldn't depend on that. In summary, so we need these protections in several layers. We need to protect the data that comes from the storage, we need to protect it in our interface, and we need to make sure that the transit is protected. And we need to do these validations, of course, according to the business rules. We need to really think about what's valid in this, in our context. Try to restrict the storage access as much as possible. If you have passwords, they need to be hashed. If you have something very sensitive, it should be encrypted. And it should also, in that case, be authenticated, because it's possible to modify encrypted data also. It could be dependent on how hard it is, but it's definitely often possible to modify data. Unless you have authenticated encryption, you could still flip bits in the encrypted data and get the application to do weird stuff. And you should use TLS, but you should also check out which ciphers you're allowing and which TLS versions you're allowing. And that goes for the client as well. People think that they only need to limit it on the server, but if you have a client that's calling a server, you could limit which TLS versions your client allows. You could say that our client can only talk TLS 1.2, so in that case, we're not vulnerable to handshake problems in earlier SSL versions, for example. Even if the server doesn't speak SSL version 3, in that case, for example, an attacker might be able to intercept and use problems in that handshake. So, the probably most important one is limit your interfaces. Remove anything coming in and going out that shouldn't be there. It's really the simplest way to get home earlier from work and have less problems in life, is to really have very few parameters and very few return values. Thank you. Do we have any questions? I have like 2 minutes left. None? All right. Thank you very much.